All right, welcome to the last section of Chapter 3, Section 3.5, Graphing Techniques. So earlier I said you should know all of the functions like y equals 1 over x or y equals x squared, just what the graph looks like. But each of those could undergo a vertical, horizontal shift. They can undergo a compression or a stretch, and with certain changes, reflections about the x-axis, y-axis, and even the origin, which they didn't mention here. So understanding a shift of a function is, or how you change a function is going to be important to us. All right, so I want to get straight to the picture, but I just want you to see the function. So we're going to use essentially this graph, our knowledge of it. We already know what it looks like. It's half parabola. It goes through 1, 1. It goes through 4, 2. I mean, you should know this graph fairly well. What does this little plus 2 do to the graph? And to the whole function, to the whole idea of it. So what they're saying is that's a vertical shift. So they drew the graph in black here, which is a good way to do this. And so you should be able to get that image in your mind. But what happens when we have this plus 2? Well, everything is shifted too. The starting value here, it starts at 2. This point is too high, or this point's too high. Notice how I'm going just straight this way. Every point's just shifted straight up. Don't shift it at any angle, just straight up. And you've got your first shift. So you can almost close your eyes and visualize the original graph that you've known for a while shifted with this plus 2. And we do call it a vertical shift for a reason. Okay, next example, not terribly creative. They put a minus 2 instead. That would be a shift down. So take the original graph, shift it down. Notice how every point is shifted down. The shape of the whole thing shifted down because of the minus 2, where it was. Now, depending on where you put the minus and where you put the 2, things could be different. So just if it seems easy now, there's a little bit of work ahead of us. All right, so they're saying that when you add k, it's shifted upward. When you subtract a positive number k, it's shifted downward vertically. All right, horizontal shifts. Horizontal shifts are right and left. These are a little trickier because of what I call the x minus c dilemma. And the minus sign is built into this formula, but we'll get to it. All right. So they're saying, what happens if you put this inside, directly inside the argument? Well, it's not changing the y values this time. It's changing the x. So it has an effect on the x graph. And let's see. So the original graph in black is this original function. Sometimes that's an important question, right? Well, what happens with the minus 2 on the x? What happens is it shifts the graph 2 to the right. Now, some people see a minus, and they understand why it's shifting the graph along the x-axis instead of the y-axis because, everything's happening to the x. But they might have a little trouble as to why I'm shifting to the right, not left, when it says minus. In other words, I'm shifting it like what some people might consider positive 2. And I'll get to y in a next slide here, but we can see that. And same idea. If you add 2 directly to x, it makes everything happen sooner, so the graph shifts to the left. And I like to let's look at it, and I'll explain what I'm talking about. So I call it the x minus c factor. Call it the x minus c phenomenon, or x minus h. But what they're saying is the graph is shifted to the right h units when you subtract from x. So if I were to take this graph and I wanted to shift it 1, 2, 3 units to the right and create that graph, if this is the square root, this would be the square root of x minus 3. It's x minus how much you want to shift it to the right. A nice way to think of it is when you subtract 3 from x, things happen later. So they happen later down the line when you're going from left to right. When you add, you're shifting it to the left that distance. All right, so here's a combination. What is this going to do? It's going to shift the graph 1, 2, 3 along the x-axis. This plus 2 is going to shift the graph 1, 2 along the y-axis. And let's look at our image. Okay, still not there. They just shifted it 1, 2, 3 so far. Now they shifted it up. And there it is. That point that was here at 0, 0, the vertex, is now shifted to that point. Now, in a problem like this, some students have learned just to start the graph here, but this really can translate beyond parabolas. So any graph, if you shift it, if it's written this way, you should be able to shift it. So let's talk about that again. So if I got rid of the 2 and the 3, my base graph would be y equals x squared, right? If the 2 and the 3 weren't there. But since the 2 and the 3 are there, it's just a shift of that graph. And that's the way you want to think about this. All right, stretching. And the opposite of stretching is compressing. But if you want to stretch a graph, so the original graph, and here this graph is, for every x value, it's 4 times higher. It's 4 times higher. It's 4 times higher. So to do that, yep, you multiply between the equal sign and whatever the original function was. So if you put a multiplication right in there, it is a stretch along the y-axis. So vertical stretch. By the way, you can always plot points on a problem like this, so that's not taken away from you, but stretching can help you kind of visualize the what's going to happen. All right, a vertical compression is when you multiply by a fraction, or you could say divide, right? But between the equal sign and whatever the base function is, this would be the compression vertically. And this is what a compressed graph looks like, the original graph. But notice at 2, it was at 4, now it's half the height. So when you want to compress something by half, you put a half there. And it basically has to do with how much you're multiplying by. If you're multiplying by a fraction, it's a compression. If you're multiplying by a number greater than 1, it's a stretch. Horizontal, be careful. All right, because it's exactly the other way around. So if you multiply by a fraction, where are they? Okay, horizontal stretch. Yeah. Let's look at it. Well, let's get that in there. The argument of the function is x. If it's multiplied by a positive number a, the new graph, all right, so you multiply it by a, and it's if a is a positive number, let's say a is, I don't know, 3. If a is 3, notice what it's saying. It's a compression by a factor of 1/3. So if you took y equals the square root of x, and you took y equals the square root of 3x, what's going to happen is I'm going to take the original graph, but I'm going to compress it along the x-axis. So a compression responds in the opposite way on the x values as it does on the y values. You multiply by a big number, that's a bigger compression. You multiply by a number between 0 and 1, that's how you stretch along the x-axis. So a little hard to, it's easy to see once you do it, but so here's an example of a function. This 3, because it's not directly on the x, it means it's stretching the y. And this 2, because it's directly on the x, it's compressing along the x-axis. A little hard to tell they did anything because they changed the scale here. See how that's 2? But all right, now it's 6. So the original graph was, let's see if I can squeeze it on here. Well, the original graph was something like this. But because of the 3, they stretched it. So it's 3 times higher, 3 times higher. That's nice, a stretch along the y-axis. This one is a compression along the x-axis. And so the original graph must have been like this, but they compressed it. So compressing it will give you this new graph. Unfortunately, they have the different scale here. If they overlaid all of them, I think we'd see it a little bit better. But, you know, the book has plenty of examples of that. All right, how about this? A minus sign between the equal sign and the x. Not on the x, but before the x. So this, what this does is it reflects the graph in a predictable way. We call it reflecting it through the x-axis. So let's compare them. So this would be the original graph. I like this one right on top of each other. So this one, you know, in other words, you can see the original graph and their change. The minus sign does something very predictable. I like to say this, minus signs change quadrants. So if you had this thing in the quadrant 1, you knew the minus sign was going to do something. And what it did here anyhow was it didn't change the domain, didn't change much, but it changed, I mean, you know, didn't change the graph in terms of what values work, but it did change the graph by reflecting it in the x-axis. I like to think of it this way, though. When you put a minus sign here, what happens is what was positive on the y becomes negative, and what was negative becomes positive. So the y values flip. So the thing flips where the y values change. Well, I'm not going to do that with just the y values without showing you what happens for the x values. So what if I were to put a minus sign not between the equal sign and the function, but directly on the x? This changes the graph, but it changes it the other direction, I guess. It makes the graph, it reflects the graph along the y-axis. And we have an example. All right, so the black graph is y equals x cubed. The blue graph is y equals parentheses minus x parentheses cubed. And by doing that, what I did was I reflected this graph along the y-axis, reflected it this way. Now, one thing I think they were missing there is, let's try that with square root. So what's the difference between y equals the square root of x, and we saw that one. Y equals minus the square root of x, and we got to see that one. And y equals the square root of minus x. We haven't seen this one yet, but this one is going to reflect the original graph through the y-axis. So it's going to reflect the graph this way. And the reason why that makes sense is take the number -4. If I put -4 in here, I would get, well, no answer. I'd get an error in my calculator. But if I put -4 in here, that negative is going to change it to +4, and I can take the square root. So putting a minus here changes the graph. So basically, once again, putting the minus here, it reflects it in the x-axis. Putting the minus where I put it here directly on the x reflects it in the y-axis. I don't know if the example the author gave us really emphasized the reflection in the y-axis as dramatically as it could have with a function we're even more familiar with, the square root function. You do have at least one question like this where they ask you a series of questions. So you want to shift it to the right by 3 units. That's when you subtract. You want to reflect it about the x-axis. Remember, to reflect about the x-axis, you put the minus sign here, not directly on the x, but here. And to shift it down 2 units. So once all 3 things have been done, you get this new equation. So they talk about using graphing techniques. Basically, if the 2 and the 1 weren't there, you know what the graph would look like because it's y equals x squared. And then doing something like this is the same as thinking, you can think of that as y equals 1/2 x squared. And so that would be a compression. And then you take the compressed graph and shift it up. Now, whenever you do more than one of these transformations, I always encourage students to plot a point. Plot at least one point so you know that you shifted the graph appropriately. All right. This one, they did a little bit of kind of manipulating with it. Working with the original way they gave it to you so you could kind of make everything pop. So what are they doing? They're saying they actually wanted to see x minus what. So this is telling you the shift eventually is going to be 2 units to the left because x minus 2 would be 2 to the right. This is telling you the shift is going to be up. And if I got rid of all the numbers, I guess you could think of my base graph as y equals minus the square root of x. So I'm saying it's this graph shifted in these ways. And let's go through it. So the original square root graph, put the minus sign in, you get this graph, shift it to this way, and then shift the whole thing up 1, I think, yeah, it's left. And there it is. The original graph, then reflected, because it changed points, then moved to the left, moved, and you get that. So, like I said, I always like to say, well, let me just plot 1 point. What if x were 0 in the original problem? I'd have the square root of 2. Okay, 0 is not a good choice. Let's pick -2. If I put in -2, otherwise it'd be plotting the square root of 2 or something. All right, if I put in -2, the square root of 0, which is 0 plus 1. So I should have in this -2, well, plus 1 is -1. I should have this ordered pair when x is -2, y is 1. And not only do I have that point, but it's my point of origin on this thing. So this point is that point. And it's pretty hard to believe that if you made a shift or did something wrong, that even 1 point would agree with the original graph. So 1 point is usually enough as a checkpoint. All right, but that is our graphing techniques. Looks like the end of 3.5, and that's the last section we cover in this section. So that's also the end of chapter 3.